Welcome, folks. I want to talk about Theorem 5.9 in our book, Judson, which proves that any permutation can be written as a product of disjoint cycles. So here I've drawn a permutation for you. I've drawn it in a different way. Usually I write my numbers also in sequential order on the bottom, and then all of the arrows cross. But here I didn't want a bunch of crossing arrows, so I just say that 1 maps to 3, 2 maps to 6, 3 maps to 7, etc. Let me show you how to write this permutation as a product of disjoint cycles. So you always start by seeing where 1 goes. 1 goes to 3, so I put a 3 here. And so then you ask next, where does 3 go? 3 goes to 7, so I put a 7 here. Because in cycle notation, this implies that 1 goes to 3 and 3 goes to 7, etc. Where does 7 go? Well, 7 goes to 5. Where does 5 go? 5 goes to 9. Where does 9 go? To 11. It's not so great to write 11 in this notation because, I don't mean that as 2 1s. I mean this is a single symbol, 11. All right, where does 11 go? 11 goes to 10. Where does 10 go? 10 goes back to 1. So now at this point, I can close off my cycle because in cycle notation that implies that 7 goes to 5, which goes to 9, which goes to 11, which goes to 10, and then it implies that 10 goes all the way back to 1. Okay, all of those numbers I hit, and I'm never going to see them again. I'm not yet done, though. I haven't told you where 2 goes, or where 4 goes, right? Or where 6 goes. So start with the next smallest number that hasn't yet appeared. So that would be 2, because 1's appeared, but not yet 2. And let's trace where 2 goes. So 2 goes to 6, which goes back to 2. So I close this off because in cycle notation, this implies that 2 goes to 6, which goes back to 2. All right. So I know where 1, 2, 3 go, but I don't yet know where 4 goes. So I'm going to start a new cycle with 4. And 4 goes to itself. So I just close it off. That implies that 4 goes back to itself. And then I've told you where 5 goes, 6 goes, 7 goes. I haven't told you where 8 goes. So let's start a cycle with 8. But 8 just goes to itself. So I can close off that cycle. And then I've already told you where 9, 10, and 11 go. So I'm all done, except to say, another great name for this is just 1, 3, 7, 5, 9, 11, 10, 2, 6. People often don't write these cycles of length 1. Okay, people often just omit them, as we've actually already done earlier. So it's okay if you write those cycles of length 1, but there's no need to. Let's quickly do one more example of this and then call it a day. Let's write this permutation here as a product of disjoint cycles. We always start by seeing where 1 goes, which here is 8. So let's see where 8 goes. It goes to 2. Then we see where 2 goes. It goes back to 1. So I close off the cycle. And I've already told you where 1 and 2 go, but not yet 3. So I open the cycle for 3, which goes to 9, which goes to 4, which goes to 5, which goes to 3. So I close off the cycle because it implies that 3 goes to 9, which goes to 4, which goes to 5, and then goes back to 3. And then I've told you where 1, 2, 3, 4, and 5 go, but not yet 6. So let's open a cycle starting at 6. Okay. 6 goes to 11, which goes to 7, which goes to 10, which goes back to 6. Close it off. And now I've told you where 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11 go. So I'm done. And the pattern here is that you'll hit out each element exactly once, but once you write down where an element goes, you'll never come back to that element again. And that's roughly speaking what allows us to write these in cycle notation as disjoint cycles, where there are no common elements between this cycle and this cycle, or really no common elements between any two cycles. What public questions might you have? All right, thanks so much.